There's a lake on Titan where you could walk across the surface without getting wet. Not because it's shallow, but because the liquid itself is lighter than your body. Step in and you'd float, surrounded by methane and ethane, under a sky thick with orange haze, while nitrogen rain falls upward in the low gravity. This isn't science fiction speculation. This is Saturn's largest moon, and it's the only other world in our solar system with stable liquid on its surface. For decades, scientists searched for life by following water. Mars rovers hunt for ancient riverbeds. Europa missions target subsurface oceans. The logic seemed airtight. Life needs liquid. Water is the universal solvent. Find water, find life. Then we got a closer look at Titan, and that certainty started cracking. Because Titan doesn't play by Earth's rules. Its lakes are liquid methane. Its ice is made of water harder than granite. Its atmosphere is denser than ours, and its surface temperature sits at -290 degrees Fahrenheit. Everything we thought we knew about where life could exist suddenly needed revision. The Cassini mission changed everything when it arrived at Saturn in 2004. Scientists expected Titan's thick atmosphere to hide a relatively boring surface. They were wrong. Radar imaging pierced through the haze and revealed something nobody predicted. Lakes. Hundreds of them. Concentrated near the poles, filling impact craters and ancient riverbeds. Some larger than the Great Lakes. But these weren't water. Spectroscopic analysis confirmed what seemed impossible. Liquid methane and ethane, stable on the surface, fed by a complete hydrological cycle. Titan has weather. It has seasons. It has coastlines that shift with evaporation and rainfall. It's Earth's hydrocarbon twin, running on completely different chemistry. The numbers don't make intuitive sense at first. Titan's surface pressure is about 1.5 times Earth's at sea level. That's manageable. But the temperature makes everything strange. At -290 Fahrenheit, methane behaves like water does here. It evaporates from lakes, forms clouds, falls as rain, carves river channels, and pulls back into seas. Water ice on Titan is effectively bedrock. It doesn't melt. It doesn't flow. The entire landscape is frozen water with liquid methane rivers cutting through it. Imagine continents made of ice, oceans made of gasoline, and rain that would fuel your car. This inversion creates chemistry Earth never experiences. On our planet, water dissolves salts and minerals, creating the ionic soup where biochemistry happens. On Titan, liquid methane dissolves completely different compounds. Long-chain hydrocarbons. Nitrogen-bearing molecules. Organic compounds that would be solid or gaseous here but remain liquid there. The result is a chemical laboratory running experiments Earth's environment would never allow. And that's where things get interesting for astrobiology. Traditional definitions of life hit a wall with Titan. We define life by its need for liquid water, its carbon-based chemistry, its energy metabolism. But those definitions assume Earth conditions. They assume water's unique properties as a solvent. They assume temperatures where proteins remain stable and cell membranes maintain structure. Titan violates every assumption. So either life there is impossible, or our definitions are too narrow. Scientists are increasingly betting on the latter. The concept gaining traction is called polyextremophile life. Not organisms that tolerate one extreme condition, but entities that function in an environment completely alien to Earth biology. These wouldn't be bacteria that survive cold. They'd be structures that require cold to maintain stability. They wouldn't use water as a solvent. They'd be built around methane's properties. Their metabolism wouldn't generate heat. It might consume hydrogen or acetylene, releasing methane as waste. Everything would be inverted from what we know. Cornell researcher Jonathan Lunine proposed a theoretical cell membrane that could function in liquid methane. On Earth, cell membranes are phospholipid bilayers. They work because water is polar. Head groups love water. Tail groups hate it. The result is a stable barrier that controls what enters and exits a cell. But methane isn't polar. It's nonpolar. So a methane-based membrane would need completely different chemistry. Lunine's team modeled something called an azotosome, built from nitrogen-containing compounds that self-assemble in liquid methane. Computer simulations show they'd be stable, flexible, and capable of selective permeability. They could work. But membranes are just the start. Metabolism is the harder problem. Life needs energy. On Earth, that energy comes from breaking chemical bonds or capturing photons. Both processes depend on specific temperature ranges where reactions proceed fast enough to be useful but slow enough to control. Titan's temperature is so low that most chemical reactions we rely on would effectively stop. So how could metabolism function? The answer might lie in Titan's atmosphere. Cassini detected something strange. Hydrogen gas near the surface is depleting faster than it should. Acetylene, a high-energy hydrocarbon, is also disappearing. The numbers don't add up unless something is consuming them. One hypothesis: organisms on Titan's surface are breathing hydrogen, metabolizing acetylene, and releasing methane. It's the inverse of our respiration. We breathe oxygen and release carbon dioxide. They'd breathe hydrogen and release methane. The energy yield would be tiny compared to Earth biochemistry. But in a cold, slow world, maybe tiny is enough. This metabolic model solves another puzzle. Titan's atmosphere shouldn't exist. Methane breaks down under solar ultraviolet radiation. Without a constant source, it should vanish in about 10 million years. Yet Titan's atmosphere is 5% methane, stable over geological time. Something is replenishing it. Volcanic outgassing from the interior is one explanation. But biology is another. If organisms are converting hydrogen and acetylene into methane, they'd be maintaining the atmosphere that makes their lakes possible. They'd be planetary-scale ecosystem engineers, like Earth's cyanobacteria that oxygenated our atmosphere billions of years ago. The implications stretch beyond Titan. If life can emerge in liquid methane at -290 Fahrenheit, then habitable zones around stars need redefinition. We've been searching for planets in the Goldilocks zone where liquid water exists. But methane-based life could thrive on worlds far colder, far from their stars, in conditions we've been ignoring. The number of potentially habitable worlds in the galaxy would multiply dramatically. Titan isn't just interesting because it might host life. It's interesting because it represents an entire class of worlds we haven't seriously considered. But before we get ahead of ourselves, we need to address the elephant in the room. Nobody has detected life on Titan. The hydrogen and acetylene depletion could have non-biological explanations. The chemistry might be abiotic. We're extrapolating from incomplete data, building hypotheses on top of models. This is responsible science, exploring possibilities, but it's not confirmation. Proving life exists on Titan would require either direct detection of organisms or finding chemical signatures that can't be explained any other way. Neither has happened yet. The challenge is partly technical. Titan is 890 million miles from Earth. Light takes over an hour to travel that distance. Sending a mission there requires years of transit time and landing on a surface we still barely understand. The Huygens probe, which descended to Titan's surface in 2005, lasted 90 minutes before its batteries died. It sent back images of a rocky shoreline and detected methane vapor near the surface. But it didn't carry instruments designed to search for life. We weren't ready to ask that question yet. Now we are. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive in 2034, will change the game. It's a nuclear-powered rotorcraft that will fly between dozens of locations on Titan's surface, sampling different environments and analyzing chemistry. It's designed to look for prebiotic chemistry, the organic building blocks that might precede life. But if life already exists there, Dragonfly has a chance of finding it. The mission will land near Titan's equator, in a region called Shangri-La, where sand dunes made of hydrocarbon particles stretch for hundreds of kilometers. What Dragonfly finds could reshape biology. If it detects only abiotic chemistry, that's still valuable. We'll learn about organic synthesis in exotic environments. But if it finds evidence of metabolic processes, or structures that suggest cellular organization, or chemical patterns that defy non-biological explanation, then we'll know life isn't unique to Earth's conditions. We'll know biochemistry can take radically different forms. And we'll know that searching for life in the universe needs to cast a much wider net. The search won't be straightforward. Even if organisms exist on Titan, they might not be easy to recognize. They won't have DNA. They won't have proteins as we know them. Their chemistry will be so foreign that our instruments might not know what to look for. Scientists are developing new biosignature frameworks specifically for non-water-based life. These focus on patterns rather than specific molecules. Does the chemistry show disequilibrium? Are there compounds that shouldn't coexist unless something is actively producing them? Is there complexity that seems organized rather than random? These questions guide not just Titan exploration but our entire approach to astrobiology. Because Titan is teaching us something fundamental. Life might not be rare in the universe, but familiar life might be. We've been searching for ourselves, for carbon and water organisms that look like Earth biology. Maybe that's the wrong approach. Maybe the universe is full of life, just not life we'd immediately recognize. Titan is the test case. It's the place where we'll learn whether biology is flexible enough to work in conditions that seem hostile to everything we understand. The story of Titan's lakes is really about expanding what we think is possible. Before Cassini, liquid lakes on another world seemed like science fiction. Now they're mapped and studied. Before astrobiology embraced exotic chemistry, life seemed confined to narrow conditions. Now we're modeling organisms that breathe hydrogen. The pattern keeps repeating. Our assumptions get challenged. The universe turns out stranger than we imagined. And the definition of habitable keeps stretching. That's why Europa matters even more than Titan in some ways. It's not trying to rewrite the rules. It's playing by them. Water, salt, energy, heat. The ingredients list reads like Earth's early oceans, just buried under ice instead of exposed to air. If life can start in those conditions, then every icy moon in the outer solar system becomes a candidate. And there are dozens of them. Europa orbits Jupiter every 3.5 days, locked in a gravitational dance with Io and Ganymede that stretches and compresses its interior like a stress ball. That flexing generates heat. Not from sunlight, which barely reaches Jupiter's orbit, but from tidal forces. The moon's icy shell cracks and refreezes constantly, creating a surface that looks like shattered glass held together by frozen seams. Those cracks matter because they might connect the surface to the ocean below. If water from the deep ocean occasionally rises through fractures and gets exposed at the surface, then a spacecraft could sample it without drilling through kilometers of ice. The Hubble Space Telescope detected water vapor plumes erupting from Europa's surface in 2012. Follow-up observations confirmed them. These aren't geysers in the traditional sense. They're intermittent, sporadic jets of material that shoot up to 200 kilometers above the surface before falling back down. Scientists think they originate from pressurized pockets of water beneath the ice, forced upward when stress fractures open temporarily. If a spacecraft could fly through one of those plumes and analyze the particles, it would essentially be sampling the ocean without landing. That's exactly what NASA's Europa Clipper mission plans to do. Launching in 2024, it won't orbit Europa directly because Jupiter's radiation environment is lethal to electronics. Instead, it will orbit Jupiter and make dozens of close flybys of Europa, sweeping through different regions and altitudes. Its instruments will measure the ice shell's thickness using radar, analyze the surface composition with spectrometers, and sample any plume material it encounters. The goal isn't to find life directly. It's to determine whether the conditions for life exist. But here's the tension. Europa might be habitable, but accessibility is the problem. The ice shell is estimated to be 15 to 25 kilometers thick. Drilling through that with current technology would take decades, and we don't even know if it's safe to try. The ocean below is under immense pressure. Breaking through could trigger unpredictable responses. And even if we reach the water, contamination becomes a serious concern. How do we search for alien life without introducing Earth life in the process? Enceladus doesn't have that problem. Saturn's tiny moon, barely 500 kilometers across, has plumes that are active, consistent, and accessible. The Cassini spacecraft flew through them multiple times, analyzing water vapor, salts, organic molecules, and even molecular hydrogen. That last one is critical. Hydrogen suggests hydrothermal activity on the ocean floor, reactions between water and rock that release energy. On Earth, entire ecosystems thrive around hydrothermal vents in total darkness, sustained by chemical energy instead of sunlight. If Enceladus has the same setup, it could support life. The difference between Europa and Enceladus comes down to scale and certainty. Europa is larger, has more water, and probably more stable conditions over geological time. But it's harder to study. Enceladus is smaller, might have a thinner ice shell, and actively advertises its ocean by spraying it into space. A mission to Enceladus could analyze fresh ocean material without landing, without drilling, without waiting decades for results. That's why the next generation of missions is split. NASA is focusing on Europa because it represents the best chance of a large, stable biosphere. But other space agencies and private missions are eyeing Enceladus because it's the low-hanging fruit. If life exists in either place, finding it at Enceladus would be faster and cheaper. The question is whether faster and cheaper is worth the trade-off if Europa turns out to be the richer environment. Then there's Ganymede, Jupiter's largest moon and the only moon in the solar system with its own magnetic field. It also has a subsurface ocean, possibly sandwiched between layers of ice in a structure scientists call an ice-water-ice sandwich. That's strange. Most icy moons have a single ocean layer beneath the crust. Ganymede might have multiple layers at different depths, each with different pressures, temperatures, and chemistries. If life emerged in one layer, could it spread to others? Could different layers host different kinds of organisms, each adapted to local conditions? We don't know. The European Space Agency's JUICE mission, which launched in 2023 and will arrive at Jupiter in 2031, will spend years studying Ganymede. It will map the subsurface structure, measure the ocean's depth and salinity, and search for active geology. Unlike Europa Clipper, JUICE will eventually enter orbit around Ganymede, giving it extended close-up access. If Ganymede's ocean is layered, that raises entirely new questions about how habitable environments can be structured. What unites all these moons is water and energy. Where those two exist together, life becomes possible. Not guaranteed, but possible. And the outer solar system has more liquid water than Earth does. Most of it is hidden under ice, locked away in oceans we've never seen. But it's there, and it's been there for billions of years. Long enough for chemistry to get interesting. Long enough for evolution to do its work, if the conditions are right. That's the shift happening in astrobiology right now. For decades, scientists focused on Mars because it was nearby, because it once had surface water, because it seemed like the obvious place to look. Mars still matters. But the icy moons are taking over as the primary targets for life detection because they have what Mars lost, active water systems that exist today, not billions of years ago. Mars is a fossil record. Europa and Enceladus are living environments. The challenge is patience. These missions take years to design, years to build, and years to reach their destinations. Europa Clipper won't arrive until 2030. Dragonfly won't land on Titan until 2034. JUICE won't finish its Ganymede observations until the late 2030s. We're talking about timelines that span decades. The scientists who propose these missions might retire before the data comes back. That's the reality of outer solar system exploration. It's generational work. But the payoff is proportional. If we find life on Europa, it won't just be a discovery. It will be proof that life can begin independently in multiple places. That would mean life isn't a fluke. It's a natural outcome when conditions align. And if it happened twice in one solar system, it's happening everywhere. The galaxy suddenly becomes a much more populated place, even if most of that life is microbial, hidden, and nothing like us. That's the argument some scientists are making now. Life might be common, but complex life might be rare. Intelligence might be rarer still. So the search isn't really about finding aliens we can talk to. It's about understanding whether biology is universal or exceptional. Whether life is chemistry's inevitable destination or a fragile accident that happened once and barely survived. The icy moons will answer part of that question. If their oceans are sterile, that tells us something. It means water and energy aren't enough. It means life requires additional factors we haven't identified, conditions that Earth had but these moons lack. That would narrow the search. We'd know habitable zones are smaller than we thought, that liquid water alone doesn't guarantee biology. But if we find life, even simple life, even just metabolic signatures or organic structures that suggest cellular organization, then the equation changes. Habitable becomes a much broader category. We'd start looking at moons around Uranus and Neptune. We'd reconsider rogue planets drifting through interstellar space, worlds with no star but enough internal heat to melt subsurface ice. We'd expand the search beyond solar systems entirely, into molecular clouds where organic chemistry runs wild without needing planets at all. The icy moons are teaching us to stop thinking of habitable as a single set of conditions. It's a spectrum. Earth-like is one point on that spectrum, but it's not the only one. Titan represents another point, where cold hydrocarbon chemistry might support life nothing like ours. Europa represents a third, where water exists but sunlight doesn't. Each environment selects for different biochemistries, different survival strategies, different forms. That's why the next 20 years matter so much. We're not just exploring distant moons. We're testing whether life is resilient enough to exist in places that seem impossible. Whether biology can adapt to darkness, cold, pressure, and isolation. Whether the spark that started on Earth can ignite elsewhere under completely different rules. The missions launching now will answer those questions. And once we have those answers, we'll know whether we're alone or surrounded by life we've simply been too Earth-focused to recognize. The timeline matters because space exploration doesn't move at human speed. It moves at orbital mechanics speed, budget cycle speed, engineering validation speed. You can't rush a spacecraft to Jupiter. The laws of physics don't care about your funding deadline. But while we wait for those flagship missions to arrive, something else is happening. Ground-based telescopes are getting better at analyzing atmospheres. Webb is already looking at exoplanet spectra with unprecedented detail. And closer to home, we're refining our detection methods. Learning what biosignatures actually look like when you can't land and sample directly. That's the real challenge with ocean worlds. Access. You can't just drill through kilometers of ice. Not yet. The technology exists in theory, but deploying it on Europa or Enceladus requires autonomous systems we're still developing. Systems that can melt through ice, navigate obstacles, communicate back through solid barriers, and operate for months without human intervention. NASA's been testing ice-penetrating robots in Antarctica. Harsh environment, thick ice, isolated conditions. About as close to Europa as you can get on Earth. And the results are mixed. Drilling works. Navigation works. Power management is the problem. You need enough energy to melt ice, run instruments, and transmit data. Solar panels don't help under the ice. Nuclear power is the only option, and miniaturizing that while keeping it safe enough to launch is where the engineering gets complicated. So we're caught in this strange position. We know where life might be. We have strong evidence that liquid water exists right now on multiple moons. But physically reaching those oceans is still a decade away, maybe two. That gap between knowing and confirming is where the frustration lives. Some scientists argue we should focus on Enceladus first. The plumes make it easier. You don't need to land or drill. Just fly through the eruptive jets and collect samples directly. Cassini did it accidentally. A dedicated mission could do it intentionally, with instruments designed specifically to detect biological molecules. If anything's alive in that ocean, pieces of it are being ejected into space constantly. That's sampling without the engineering nightmare of penetration. But plume analysis has limits. You're collecting fragments, not context. You might find organic molecules, but are they biological or geological? You might detect chemical disequilibrium, but is that metabolism or just weird chemistry? Without direct observation, without being able to see how these molecules are organized or whether they're part of larger structures, interpretation becomes guesswork. That's why Europa Clipper is carrying multiple instrument types. Cameras to map the surface. Spectrometers to analyze composition. Ice-penetrating radar to probe the subsurface. Magnetometers to confirm the ocean's conductivity. No single measurement proves life. But patterns across multiple datasets can build a case strong enough to justify the next mission, the one that actually lands. And that landing mission is already being designed. Europa lander is still in concept phase, but the basic plan is clear. Touch down on a geologically active region. Deploy sensors to listen for subsurface activity. Use a drill or melt probe to access material just below the surface, where radiation hasn't destroyed organic molecules. Run chemical tests on site. Look for amino acids, lipids, metabolic byproducts. Anything that suggests biological processes rather than sterile chemistry. The landing site selection will be critical. Too smooth and you're probably on old ice, far removed from recent ocean contact. Too rough and landing becomes impossible. The ideal target is somewhere recent resurfacing has occurred. Cracks, ridges, areas where tidal flexing has pushed fresh material upward. Those are the places where ocean chemistry meets the surface, where contamination from space radiation is minimal. Radiation is the other problem no one talks about enough. Jupiter's magnetic field accelerates charged particles to extreme energies. Europa's surface gets bombarded constantly. Organic molecules don't survive that. They break apart, rearrange into non-biological forms. Which means surface sampling alone won't work. You need to dig, even if it's just a meter or two, to reach material that's been shielded. That complicates the mission profile. Now you're not just landing, you're drilling in a place where your equipment might freeze, where communication delays mean full autonomy, where one mechanical failure ends the mission. The engineering margins are razor thin. Which is why Europa lander keeps getting delayed. It's not lack of interest. It's physics. While engineers solve those problems, astrobiologists are asking harder questions. What does alien life even look like? We assume cells, membranes, metabolism. But that's Earth bias. Life here evolved in specific conditions with specific chemistry. Carbon-based, water-dependent, DNA-encoded. Those aren't universal requirements. They're just what worked here. Titan suggests alternatives are possible. Liquid methane isn't water. It doesn't have water's properties. But chemistry still happens. Molecules still interact. Energy still flows through systems. Whether that produces something we'd recognize as life is the open question. But the fact that we're asking it means our definition of life is expanding. Some researchers propose we should stop looking for Earth-style biology and start looking for thermodynamic signatures instead. Life, at its core, is a system that maintains disequilibrium. It takes in energy, uses it to build structure, and exports entropy. That's true whether you're a bacterium, a tree, or a hypothetical methane-based organism on Titan. The chemistry changes, but the thermodynamics don't. If that's the framework, then detection becomes different. You're not searching for DNA or proteins. You're searching for organized complexity. Patterns that persist against entropy. Chemical gradients that shouldn't exist unless something is actively maintaining them. That's harder to measure from orbit, but it's also harder to misinterpret. This shift in thinking is changing mission design. Future landers won't just carry microscopes and chromatographs. They'll carry calorimeters to measure heat flow, sensors to detect chemical cycling, instruments that can recognize complexity without assuming specific molecular structures. We're preparing for life that doesn't look like us. Which brings up the philosophical side. If we find microbial life on Europa, how do we treat it? Do we have ethical obligations to extraterrestrial microbes? The Outer Space Treaty says we can't contaminate other worlds, but it's vague on what contamination means. Bringing Earth bacteria to Europa would be catastrophic for any native ecosystem. But is accidentally killing alien microbes during sampling any different than what we do in Earth's deep oceans every time we take a core sample? These aren't abstract questions. They'll become policy decisions the moment we confirm life exists elsewhere. Some scientists argue for extreme caution. Observe from orbit, never land, preserve these environments in their natural state. Others argue that's impractical. We can't understand life without direct study. Sterilization protocols exist for a reason. Use them properly and contamination risk drops to near zero. The debate will intensify as missions get closer to launch. Right now it's academic. But when Europa lander is sitting on a launch pad, fully fueled, and someone raises concerns about planetary protection, the conversation becomes real. Do you scrub the mission? Redesign the protocols? Accept calculated risk? There's no consensus yet. What's clear is that finding life on an icy moon would be simultaneously the greatest discovery in human history and the beginning of much harder questions. Not just scientific questions, but ethical ones. Legal ones. Questions about how we interact with biology that exists beyond our planet, that evolved independently, that has no concept of humanity and no stake in our survival. That's the weight these missions carry. They're not just exploring. They're potentially introducing us to a second genesis, a separate origin of life that followed different rules and produced different results. Even if it's just bacteria. Even if it's chemically simple. The implications reshape everything we thought we knew about biology's place in the universe. And if multiple moons harbor life, if Europa has one form and Enceladus has another and Titan has a third, then we're not looking at rare accidents. We're looking at inevitability. Life becomes something the universe does regularly, under wildly different conditions, using whatever chemistry is available. That's a different cosmos than the one we grew up in. The icy moons are forcing us to confront that possibility before we're ready. Before we have the technology to fully investigate. Before we've agreed on what finding life even means. We're in this strange transition period where we know enough to ask the right questions but lack the tools to answer them definitively. So we build the tools. Design the missions. Train the next generation of scientists who'll interpret data we haven't collected yet. That's where we are now. Poised between knowing these worlds exist and understanding what they contain. The gap is closing, but slowly. And every year that passes without confirmation is another year of uncertainty, another year where life beyond Earth remains theoretical rather than observed. The timeline matters here. Europa Clipper launches in October 2024. JUICE, the European Space Agency's Jupiter mission, launched in April 2023. Both arrive at Jupiter in the 2030s. They'll spend years mapping, measuring, taking data we don't have yet. But neither lands. Neither drills. They're reconnaissance, not contact. The actual moment when we touch Europa's ice and sample its ocean, that's still decades away, potentially 2040s or 2050s, depending on funding, technology development, and political will. Which means most of the scientists designing these missions won't see the final results. They're building instruments for questions that'll be answered by people who haven't finished grad school yet. That's normal in planetary science. Voyager launched in 1977 based on calculations done in the 1960s. The researchers who planned those trajectories were working with slide rules. Now we're analyzing data from those same spacecraft 47 years later. Long timelines are standard, but they create a strange disconnect. Public excitement peaks during launches, during flybys, during press conferences with new images. Then it fades. The actual science happens in the gaps. Years of orbital mechanics, incremental data collection, slow refinement of models that nobody outside the field pays attention to. Europa Clipper will make 49 close flybys of Europa over 4 years. Each flyby generates gigabytes of data. Radar soundings, ice-penetrating measurements, magnetic field readings, surface composition maps. That data gets analyzed, peer-reviewed, published in papers with titles like High-Resolution Subsurface Characterization of Europa's Chaos Terrain Using Multi-Frequency Sounding. Not exactly viral content. But that's where the discoveries happen. Not in dramatic announcements, but in cumulative understanding built dataset by dataset. Someone notices an anomaly in the magnetic readings. Someone else correlates it with a surface feature. A third researcher runs simulations and realizes it matches what you'd expect from a subsurface current. Suddenly you've constrained the ocean's salinity and temperature in one specific region. That's progress. Unglamorous, incremental, but real. The challenge is maintaining momentum across decades. Keeping missions funded when results are slow. Convincing politicians that orbital surveys matter even when they don't produce headlines. NASA's good at this. They've kept missions running for years past their planned lifetimes because the science justifies it. Cassini was supposed to study Saturn for 4 years. It lasted 13. The Opportunity rover was designed for 90 days on Mars. It operated for 15 years. Once a mission is active and producing data, shutting it down becomes harder to justify. But getting to that point requires sustained investment through the unglamorous phases. Europa Clipper costs $4.25 billion. That's over 2 decades of development, construction, launch, and operations. For context, that's roughly what the U.S. spends on military operations every 3 days. It's less than the budget for a single aircraft carrier. In terms of national spending, it's a rounding error. But it still requires congressional approval, annual budget fights, competing priorities. Every year without a major discovery is a year someone argues the money could go elsewhere. The counterargument is simple. This is a one-time cost for potentially permanent knowledge. If Europa has life, we learn that once and it changes biology forever. If it doesn't, we learn that too, and it narrows where else to look. Either outcome justifies the investment. But that logic doesn't always win budget battles. Which is why mission designers build in public engagement. Pretty pictures from JunoCan. Visualizations of what Europa's ocean might look like. Educational outreach explaining why this matters. It's not just science communication. It's survival strategy. Missions with public support get continued funding. Missions that fade from public consciousness get cut. So there's this weird tension. The actual science is slow, technical, incremental. But the presentation has to be exciting, accessible, urgent. Researchers have to be both rigorous scientists and effective communicators. Not everyone's good at both. Some of the best planetary scientists are terrible at explaining their work to non-specialists. Some of the best science communicators oversimplify to the point of inaccuracy. Finding people who can do both is rare and valuable. NASA knows this. They fund media specialists, visualization teams, outreach programs specifically to keep missions in public awareness. It works. Curiosity rover has a Twitter account with millions of followers. People care about a robot on Mars because someone made them care. The same strategy applies to Europa. Make people invested in the search for life on an ice-covered moon 48 light minutes from Earth. Make them check for updates. Make them explain to their kids why this matters. That cultural investment translates to political support when budget renewals come up. But it only works if the underlying science is solid. You can't sustain interest in a mission that's not producing results. Which brings us back to the question. What if Europa Clipper finds nothing? What if the ocean's sterile? What if years of flybys show no biosignatures, no organic chemistry, no signs that life ever existed there? That's a possible outcome. Not the one anyone wants, but scientifically valid. It would tell us something important. That liquid water and energy sources aren't enough. That you need additional factors we haven't identified yet. Maybe the ocean's too young. Maybe the chemistry's wrong. Maybe life requires conditions that only Earth provides. That would be disappointing but not catastrophic. Science advances through negative results as much as positive ones. Ruling out possibilities narrows the search space. If Europa's dead, we focus on Enceladus. If that's sterile too, we rethink our assumptions about where life can form. The worst outcome isn't finding nothing. It's ambiguity. Detecting organic molecules that could be biological or geological. Finding chemical gradients that might indicate life or might just be mineral dissolution. seeing surface features consistent with biology but not definitive. That's the scenario that drives scientists crazy. Spending billions, traveling for years, collecting massive datasets, and ending up with maybe no clear answer. Just more questions. It's possible. Maybe even likely. Biology's messy. It doesn't announce itself clearly unless you're looking at something obviously alive. Microbes don't leave business cards. They leave chemical traces that could have multiple explanations. Distinguishing between biotic and abiotic processes in an alien environment with limited data is hard. Sometimes impossible without direct sampling, which we can't do from orbit. So we might end up in limbo. Strong suggestions but no confirmation. Enough evidence to justify a lander mission but not enough to declare victory. That's actually the scenario most researchers expect. Not a clear yes or no, but a probably, pending further investigation. That's how science usually works. You don't get revelation. You get provisional conclusions that get refined as new data arrives. The public doesn't like that. They want definitive answers. Life exists or it doesn't. Tell us which. But reality's more complicated. We might spend the next 50 years saying Europa probably has life, without being able to prove it conclusively. Living in that uncertainty requires patience. Something modern culture isn't great at. We want answers now. We want streaming video from Europa's ocean floor showing alien fish swimming past the camera. That's not happening. What we get is spectroscopy data suggesting complex organic molecules. Magnetic field variations consistent with conductive fluids. Plume compositions showing water-soluble compounds that might support metabolism. All circumstantial. All suggestive. None definitive. And we sit with that. Publish papers. Debate interpretations. Design better instruments for the next mission. That's the actual process. Not dramatic. Not cinematic. Just methodical accumulation of evidence toward increasingly confident conclusions that might take decades to reach. The icy moons force us to accept this pace. They're not going anywhere. Europa's been there for 4 billion years. It'll wait another 50 while we figure out how to study it properly. The urgency is artificial. We want answers because we're curious, but the universe doesn't care about our timeline. It operates on geological scales. Orbital periods measured in days. Ocean circulation measured in centuries. Evolutionary processes measured in millions of years. Our 70-year human lifespans are nothing against that backdrop. Which makes this whole endeavor slightly absurd. Temporary biological creatures trying to understand permanent planetary processes. Using instruments that'll fail in a decade to study worlds that have existed since the solar system formed. It's audacious when you think about it. But that's what exploration is. temporary beings pushing against the limits of temporary understanding. Each generation builds on what the previous one learned. Each mission answers some questions and creates new ones. The researchers working on Europa Clipper won't see the lander mission. The people designing the lander won't see the submarine mission. The submarine designers won't see the deep drilling mission. But each step makes the next possible. That's how you explore an alien ocean from 500 million kilometers away. Slowly, carefully, one impossible step at a time. Which brings us to the uncomfortable truth nobody wants to discuss. The probability calculation. What are the actual odds we find life on Europa? Not, is it there, but, will we detect it if it is? Those are different questions. Completely different. Life could exist in Europa's ocean and we might never know. The ocean's huge. 100 kilometers deep in places. Volume exceeding all Earth's oceans combined. And we're sampling tiny fractions. A few plume passes. Some surface spectroscopy. Maybe eventually a lander analyzing 1 square meter of ice. That's like trying to find whales by analyzing a single drop of seawater from the Atlantic. Possible. Technically. Likely? No. Europa's ocean could be teeming with microbial life and our instruments might sample a barren region. Or life might cluster around specific hydrothermal vents we never get close to. Or organisms might be seasonal, dormant during our observation window. Or they might exist in forms our instruments aren't designed to detect. False negatives are a massive problem in astrobiology. You can't prove something doesn't exist just because you didn't find it. You only sampled one location at one time with one set of instruments looking for one type of biosignature. Negative results tell you almost nothing. Which means even if Europa Clipper finds nothing conclusive, the question remains open. The mission could be scientifically successful and still leave us uncertain. That's not failure. That's just reality. But here's where it gets interesting. Absence of evidence starts mattering after enough missions. One negative result means little. 5 missions over 30 years finding nothing. That shifts probabilities. Not to 0, but lower. The Bayesian calculation changes with each data point. Right now, before we've really looked, the prior probability is genuinely uncertain. Some researchers estimate 50-50 odds. Others think it's more like 10%. Nobody knows. Too many variables. But as missions accumulate data, the probability distribution narrows. Either life's signature becomes increasingly apparent or increasingly unlikely given what we're seeing. The frustrating part is how long this takes. Decades of missions. Billions in funding. All to narrow the probability range from maybe to probably or probably not. That's slow. Expensive. Uncertain. And absolutely necessary. Because finding life elsewhere, even microbial life in an alien ocean, changes everything. Not technologically, not immediately practically, but philosophically. It answers whether biology is a cosmic inevitability or a singular accident. If Europa has life, and Enceladus has life, and maybe Titan has life, then life's everywhere. Any world with liquid water and chemical energy probably develops biology eventually. The universe is living. We're not alone. Not even close. That shifts how we see ourselves. Earth stops being special. Life stops being precious and rare. It's just chemistry that happens when conditions permit. Common, expected, ordinary. Some people find that comforting. Others find it diminishing. Either way, it's transformative. But what if we look and find nothing? What if Europa's ocean is sterile? What if all the icy moons are dead? That's equally important, maybe more so, because it suggests life's harder than we think. That liquid water and energy aren't enough. That something else is required. Some additional ingredient or condition we haven't identified. And Earth has it, but these ocean worlds don't. That makes Earth remarkable again. Not for having water or chemistry, but for crossing some threshold these other worlds couldn't reach. And we don't know what that threshold is. Both answers matter. Life everywhere changes our cosmic perspective. Life nowhere changes it differently. We learn something fundamental either way. Which is why these missions matter despite the uncertainty. Despite the slow pace. Despite the ambiguous results we'll probably get. This isn't about satisfying curiosity, though that's part of it. It's about understanding the universe's capacity for biology. Whether life is chemistry's inevitable consequence or a profoundly improbable accident that happened exactly once. We can't answer that from Earth. We have to look elsewhere. And the icy moons are the closest, most accessible elsewhere we've got. So we build the missions. Design the instruments. Wait years for the data. Interpret ambiguous results. Propose follow-up missions. Wait again. It's tedious. It's expensive. It's uncertain. And it's the only way forward. Now here's something nobody talks about. The contamination problem going both directions. We worry constantly about forward contamination. Bringing Earth microbes to Europa and ruining the pristine alien environment. Every spacecraft gets sterilized. Components baked. Procedures documented. All to avoid accidentally seeding Europa with terrestrial biology. That's responsible. Necessary. But it assumes Europa's biology, if it exists, is vulnerable to Earth organisms. That our microbes could survive there. Outcompete native life. Establish themselves. Maybe. Maybe not. Europa's ocean is extreme by Earth standards. High pressure. Low temperature. Strange chemistry. Earth organisms aren't adapted to that. They'd probably die quickly. The environment might be naturally hostile to anything from our biosphere. But we don't know. So we sterilize anyway. Better safe than sorry. But here's the reverse question nobody asks. What if Europa's biology is dangerous to Earth? What if we bring samples back and they contain organisms that thrive here, that outcompete terrestrial microbes, that lack natural predators or environmental constraints? Invasive species are devastating on Earth when introduced from other continents. Imagine invasive species from another world, with completely different biochemistry, no natural checks, no evolutionary relationships with anything here. That could be catastrophic, or completely harmless. We don't know because we've never encountered alien biology. Sample return missions have to account for this. Containment protocols, quarantine procedures, analysis in isolation before exposure to Earth's environment. It's complicated, expensive, possibly excessive if Europa's organisms can't survive here, but possibly essential if they can. The irony is we might discover life on Europa and still never bring samples to Earth because the contamination risk is too high. We'd study it remotely, send instruments instead of returning material, keep the biospheres separate. That's frustrating from a research perspective. You want the samples. You want to analyze them properly in fully equipped laboratories. But you can't risk contaminating Earth's biosphere or Europa's. So you're stuck doing science at arm's length. Forever. Unless we develop methods to completely neutralize biological material while preserving its chemical and structural information, then you could safely return samples. But that technology doesn't exist yet, and might not be possible. The universe is full of these practical barriers. Not just technical challenges, but fundamental constraints that can't be engineered around. Another constraint nobody mentions: political continuity. These missions take decades. Decades of funding, consistent support across multiple administrations, different political parties, changing budget priorities. Europa Clipper survived because it had bipartisan support. But that's rare. Most long-term projects get canceled halfway through when priorities shift. New administration comes in, wants different flagship missions, cuts funding for the previous administration's pet projects. Science doesn't work on 4-year election cycles. It works on 20-year development timelines. Those don't align well, which means we need international collaboration. Spreading the cost and commitment across multiple space agencies so no single election can kill the program. ESA, NASA, JAXA working together. That's how you sustain multi-decade efforts. But international collaboration is slow, complicated, requires diplomatic negotiation, technology sharing agreements, export control compliance. It's a mess. Yet it's necessary. No single country wants to fund a $10 billion program alone, especially when the payoff is uncertain and decades away. So we partner, compromise, negotiate, and slowly build missions that might survive long enough to reach their targets. Assuming nothing breaks. Assuming budgets hold. Assuming political will persists. Those are big assumptions. Most proposed missions never happen. They get studied, designed, prototyped, then canceled when funding dries up, or priorities change, or technical problems emerge that push costs too high. The graveyard of canceled missions is vast. Europa Orbiter, Titan Mare Explorer, Enceladus Life Finder, all studied seriously, all canceled before construction began. Europa Clipper is rare because it survived that process, made it through design reviews, secured funding, actually launched. That's exceptional. And even now, there's no guarantee future missions will follow. Clipper could be the only Europa mission in our lifetime. The lander might never happen. The submarine definitely won't happen anytime soon. We might get one shot at this. One spacecraft. One dataset. And that's all. Which means interpreting that data becomes absolutely critical. Extracting every possible bit of information. Because we might not get another chance. The pressure on researchers is intense. They've waited careers for this mission. It has to work. The instruments have to function. The data has to be interpretable. Because if something fails, if results are ambiguous, there might not be a follow-up mission to clarify things. You get one chance to answer whether life exists beyond Earth. And the answer might be insufficient data. That's what keeps researchers awake at night. Not technical failure, though that's bad enough, but ambiguous success. Data that suggests something interesting but doesn't confirm anything. Living in that uncertainty for the rest of your career. Knowing the answer might exist in an ocean you can see but can't reach. That's the real challenge of exploring Europa. Not the engineering, though that's hard. Not the distance, though that's vast. But the fundamental limitation that you're trying to answer the biggest question in biology with indirect measurements of a world you can't fully access. And you might only get one attempt. Yet here's what makes Europa Clipper historically significant regardless of what it finds. It establishes the methodology. Creates the template for how you study ocean worlds remotely. Every instrument, every measurement technique, every data analysis approach becomes a blueprint. Future missions to Enceladus, Titan, Ganymede, they'll build on this foundation. We're learning how to read these worlds. developing the language needed to interpret what subsurface oceans tell us through their ice shelves. That knowledge persists even if this specific mission doesn't find life. The techniques remain useful. The calibration data becomes reference material. Understanding how ice responds to tidal heating, how salts concentrate in fractures, how plumes form and dissipate, all of that applies broadly. You're not just studying Europa. You're studying the physics of ocean worlds as a class. Which means even negative results have value. Knowing that Europa's ocean doesn't show biosignatures tells you something about where life can and can't emerge. Constrains the parameters. Narrows the search space for future efforts. Science progresses through elimination as much as discovery. And there's another angle nobody discusses much. The cultural impact of searching. The fact that humanity allocated resources, launched a spacecraft, spent years trying to answer whether we're alone. That matters philosophically even before we have results. It demonstrates what our species considers worth pursuing. Shows that curiosity about our place in the universe ranks high enough to justify significant investment. That's not trivial. In a world focused on immediate returns, quarterly earnings, election cycles, committing to a multi-decade search for extraterrestrial life represents something different. Long-term thinking, valuing knowledge for its own sake. That cultural statement matters. It influences how future generations think about science funding, about exploration, about what questions deserve sustained effort. Europa Clipper becomes part of that narrative. A marker of what early 21st century humanity chose to prioritize. Decades from now, regardless of what it finds, people will look back at this mission as a moment when we seriously attempted to answer the life question. That attempt matters. The audacity of it. The technical sophistication required. The international cooperation involved. All of that represents something worth doing even if the answer turns out to be, we still don't know. Because the pursuit itself drives innovation. Problem solving at this level creates spillover benefits. Radiation-hardened electronics developed for Clipper get used in other applications. Power systems designed for distant operation become templates for future spacecraft. Instruments built to detect faint biosignatures find uses in earth science, medical diagnostics, materials analysis. The engineering doesn't vanish if the science proves inconclusive. It propagates, gets refined, applied elsewhere. NASA's Technology Transfer Office exists specifically to move space-developed innovations into commercial markets. So taxpayer investment in missions like Europa Clipper generates returns beyond the immediate science. Though that's not why we do it. We do it because the question is fundamental. Does life arise wherever conditions permit? Or is Earth a cosmic fluke? That question shapes how we understand our existence. Informs philosophy, theology, ethics. Changes what it means to be alive if we discover we're not unique. Or confirms our isolation if we search thoroughly and find nothing. Either answer matters profoundly. And you can't get that answer without looking. Without building spacecraft. Without making measurements. So we build Europa Clipper. Launch it toward Jupiter. Wait years for data. Knowing the answer might not be clear. Might require follow-up missions. Might remain ambiguous for decades. We do it anyway. Because some questions are worth asking even when answers aren't guaranteed. Even when the timeline extends beyond single careers. Beyond political cycles. Into time frames that test institutional patience. The commitment itself becomes the statement. We care enough to try. To invest resources. To sustain focus across years. That says something about humanity worth acknowledging. Now let's address what happens if Clipper does find something. If measurements suggest biological activity, what then? The discovery process would be slow, deliberate. Multiple independent confirmations required before announcing anything. You don't claim extraterrestrial life based on single data points. You need patterns, consistency, elimination of alternative explanations. That takes time. Months of analysis. Years potentially. Researchers would be cautious to the point of paranoia. Extraordinary claims require extraordinary evidence. The standard for claiming life detection is deliberately high. So initial findings would be tentative. Suggestive rather than conclusive. Papers would use careful language. Consistent with biological processes. Difficult to explain through known abiotic mechanisms. Nothing definitive until the evidence becomes overwhelming. And even then, debate would continue. Scientists arguing over interpretation. Alternative hypotheses proposed. Demands for additional data. That's healthy. That's how science works. Skepticism until proof becomes undeniable. But assuming evidence accumulates. Multiple lines of data pointing the same direction. Consensus gradually forming that biological explanation is most likely. What happens then? First, immediate calls for follow-up missions. Sample return if possible. More sophisticated instruments. Direct access to the ocean. Funding would materialize. Political support would surge. Nothing motivates space agencies like the possibility of confirming life beyond Earth. Budgets that seemed impossible suddenly become feasible. Timelines that were decades long get compressed. National prestige enters the equation. Countries want to be part of the discovery. International collaboration intensifies. Everyone wants involvement in the biggest scientific finding in human history. Because that's what it would be. Confirmation of extraterrestrial life rewrites biology. Establishes that Genesis isn't unique. That the universe creates life wherever chemistry permits. The implications cascade through every field. Philosophy grapples with what it means. Theology adjusts frameworks. Ethics considers how we treat non-Earth life. Law debates who owns extraterrestrial organisms. Policy determines contamination protocols. It's not just science. It's civilization-level adjustment. And it starts with measurements from a spacecraft orbiting Jupiter. Data transmitted across hundreds of millions of miles. Interpreted by researchers who've dedicated careers to this question. That's the scenario Europa Clipper could enable. Not guaranteed. Maybe not even likely. But possible. And possibility is enough. Enough to justify the mission. The investment. The decades of work. Because if there's even a small chance of answering whether we're alone, you take it. You build the spacecraft. Launch it. Wait for data. Accept that results might be ambiguous. That follow-up might be needed. That certainty might take generations. You do it anyway. Because some questions define what it means to be human. Our need to understand our place in the universe. To know if life is rare or common. Special or inevitable. Those questions don't have dollar values. Can't be justified through economic analysis. They're justified by being fundamental. By mattering in ways that transcend normal metrics. Europa Clipper represents that kind of question. Pursued seriously. With sophisticated tools. Real commitment. And now we wait. Years of flight time. Then years of data collection. Followed by years of analysis. The answer, if it comes, won't arrive quickly. Won't be simple. Might not even be definitive. But we'll know more than we do now. Understand ocean worlds better. Have methods for detecting biosignatures. Possess data to guide future missions. That's progress. Incremental. Frustrating. Necessary. The only way forward when you're trying to explore worlds you can't physically reach. When you're searching for life that might not exist. Or might exist but remain undetectable with current methods. You build what you can. Measure what's possible. Interpret carefully. And prepare for the likelihood that this is just the beginning. That Europa Clipper is the first chapter in a much longer story. One that might not conclude in our lifetimes. But one worth starting. Worth pursuing. Worth the investment of resources and decades of effort. Because ultimately, the question of whether life exists beyond Earth isn't just scientific curiosity. It's existential inquiry. Who are we? Where do we fit? Is intelligence common or rare? Those questions shape everything. And Europa, with its vast subsurface ocean, represents our best near-term chance at answers. So we send Clipper. We wait. We analyze. We accept uncertainty, and we continue the search. Because that's what drives us forward. Not certainty of success, but the possibility of discovery. The chance that somewhere beneath those ice sheets, in the dark cold ocean, something lives. Something that proves we're not alone. That life finds a way. That the universe is richer and stranger than we imagined. And if we're wrong, if Europa is sterile, then we search elsewhere. Enceladus, Titan, exoplanet oceans. The search continues. Because now we know how to look, what to measure, how to interpret. Europa Clipper taught us that. Made us better at reading worlds we can't touch. And that knowledge compounds, gets refined, applied to the next target, then the next. Until eventually, maybe decades from now, maybe centuries, we find what we're looking for. Or confirm we're alone. Either way, we'll know. And knowing matters. That's what Europa Clipper is really about. Not just one mission, but the beginning of systematic search. The moment humanity decided to seriously pursue the life question, using the best tools we have, accepting the limitations, pushing forward anyway, because some answers are worth waiting for. So we're left in this strange position, waiting. Years of flight time ahead, then years of data collection, followed by years of analysis where researchers argue over interpretation and demand additional measurements before committing to conclusions. The answer won't arrive as a headline, won't be a single dramatic announcement. It'll emerge gradually through accumulated evidence, refined models, eliminated alternatives. Messy, uncertain, requiring patience nobody wants to exercise. But that's exploration at this scale. You don't get instant gratification. You get slow revelation. Data points that individually mean little but collectively suggest something profound. And maybe that's appropriate. Maybe the biggest question in biology shouldn't have a quick answer. Maybe it should require decades of effort, billions in investment, international collaboration, technical innovation we haven't achieved yet. Because if the answer comes easy, it probably isn't the right answer. Europa's ocean has existed for 4 billion years. It's not going anywhere. The question of whether life exists there has waited this long. It can wait longer while we develop proper methods to investigate. The urgency is ours, not the universe's. We want to know before we die. Want to see the answer in our lifetimes. But cosmic processes don't care about human lifespans. They operate on geological timescales, evolutionary timescales. Timelines measured in millions of years while we measure in decades. So we do what we can. Build missions that might outlast us. Collect data future researchers will analyze. contribute to understanding that compounds across generations. That's the actual nature of this search. Not individual achievement but collective progress. Each mission adds pieces. Each dataset refines models. Each generation pushes a little further than the last. Europa Clipper is one piece. Important, but not final. It'll answer some questions and create others. Suggest follow-up investigations. Provide data that becomes more valuable over time as we develop better interpretation methods. Maybe it finds biosignatures. Maybe it doesn't. Either way, it establishes the framework. Shows what's possible with current technology. Identifies what improvements are needed. And then we build the next mission. Better instruments. Different approach. Closer access. The process continues until we have definitive answers or exhaust feasible investigation methods. That could take 50 years. Could take a century. Could take longer than human civilization persists in its current form. But the question remains worth asking. Worth pursuing. Worth the investment even knowing answers might not arrive in our lifetimes. Because this is what separates us from every other species on Earth. This capacity to ask questions whose answers we might never see. To pursue knowledge that benefits future generations more than ourselves. To invest in understanding purely because understanding matters. Europa's ocean holds secrets 4 billion years old. Secrets about whether life is inevitable or exceptional. Whether biology is chemistry's natural outcome or a fragile accident that happened once. We're trying to read those secrets from hundreds of millions of miles away. Using instruments that can't touch what they're studying. Interpreting signals that could mean multiple things. It's audacious. Maybe impossible. Definitely worthwhile. The search for life beyond Earth isn't just science. It's philosophy. It's existential inquiry about our place in the universe. Whether we're alone or surrounded by biology we haven't recognized yet. And we won't know until we look. Really look. With sophisticated instruments, sustained effort, decades of patience. That's what Europa Clipper represents. Not just a spacecraft. Not just a mission. But humanity's commitment to answering the biggest question we can ask. Are we alone? The answer is out there. Beneath ice sheets on distant moons. In subsurface oceans we can't access. In chemistry we don't fully understand. And we're going to find it. Not today. Not tomorrow. But eventually. Because that's what we do. We explore. We question. We search. Even when answers take decades. Even when results are ambiguous. Even when success isn't guaranteed. We send spacecraft to frozen moons. We measure magnetic fields and analyze plume chemistry. We build instruments that might detect life completely unlike ours. And we wait. Years. Decades. However long it takes. Because some questions are worth answering regardless of how long they take. Some knowledge is worth pursuing even when you might not live to see it confirmed. Europa's ocean is still there. Still hidden. Still holding whatever secrets it contains. And somewhere between now and whenever those secrets are revealed, we'll keep searching. Keep measuring. Keep pushing the boundaries of what's possible. That's the real story of Europa Clipper. Not what it finds, but what it represents. Humanity reaching toward understanding, refusing to accept ignorance about our place in the universe. The data will come back, slowly, over years. We'll analyze it, debate it, build new missions based on what we learn. And eventually, maybe not in our lifetimes but in someone's, we'll know. We'll have the answer. Until then, we wait. And we search. Because that's what drives us forward. Not certainty, but possibility. The chance that beneath those ice sheets, in the dark cold ocean, something lives.